Situations where an amount decreases by a constant percent can be modeled with exponential decay equations. From figuring out the age of prehistoric monuments like Stonehenge, to analyzing a cooling cup of coffee, exponential decay occurs in a wide variety of situations. Perhaps it will even help us survive a zombie virus. Zombine is rumored to be a radioactive substance that can be used to treat zombies and transform them back into humans. Unfortunately, it is very harmful to the individual taking it with very undesired side effects. However, the substance decays or disappears from the bloodstream very rapidly, about 43% every day. In this lesson, we will analyze this exponential decay situation with tables, graphs, and equations. Let's start with tables. Fact: Zombine decays 43% each day. That disappears little by little from our bloodstream. Patients are given a one-time dosage of 65 milligrams. So patients begin with 65 milligrams of Zombine in their system. To figure out how much Zombine remains in their bloodstream after one day, we need to figure out the multiplier for a 43% decrease. Well, 43% equals 0.43. And that means that each day your bloodstream keeps 57% of the bromine. So our multiplier will be 0.57. After one day, patients have 37.1 milligrams of Zombine in their blood system. After 2 days, 21.1 milligrams. So every day the patient is losing 43% of the Zombine in their bloodstream. But that means they're keeping 57% of the Zombine in their bloodstream. So our multiplier is 0.57. Let's turn this data into a graph so we can see what this exponential decay looks like. First, let's scale our axes. We'll put days on the horizontal axis. Put milligrams of Zombine on the vertical axis. We need to go up past 65. That's the largest amount of Zombine in our blood system. So why don't we go by tens and go up to 70? Now we can make our graph and see what this exponential decay model looks like. Let's connect these points with a smooth curve. With exponential decay graphs, you have to be really careful about how you draw the tails. Notice here that the milligrams of Zombine in our system will never become negative milligrams, so we don't want our graph to cross below the x-axis. Now that we have our graph, let's try to figure out an equation. Let's look at a pattern that will help us figure out an exponential decay equation without memorizing a formula. On day 0, we have 65 milligrams. To figure out how many milligrams of Zombine we have after one day, we'll multiply by 0.57, because that's our multiplier. We have 57% of the Zombine left in our system each day. On day 2, we're going to multiply by 0.57 again. I'm going to leave it written out the long way so we can see a pattern. So after day 2, we only have 57% of what we had after day 1. And on day 3, probably by now we see a pattern emerging. We need to multiply by 0.57 again, because we only have 57% of what we had after day 2. And after day 4, we need to multiply by 0.57 again. Fortunately, there's a better way to write expressions like these. We can use exponents to represent repeated multiplication. So on day 4, that equals 65 times 0.57 to the 4th power. And on day 3, 65 times 0.57 to the 3rd power. And on day 2, 65 times 0.57 to the 2nd power. It even works on day 0, because 65 equals 65 times 0.57 to the 0 power, since anything to the 0 power equals 1. Let's look for a pattern here. Maybe it will help us write an equation. On day 4, we notice that the expression to get the milligrams of Zombine is 65 times 0.57 to the 4th power. And on day 2, it's 65 times 0.57 to the 2nd power. The exponent matches the day. That's pretty convenient. So let's extend this and say we have day x. Well, that would be 65 times 0.57 to the x power. And that would tell us how many milligrams of Zombine we have left in our system after any number of days. Looks like we have our equation. Let's take a closer look at our Zombine equation. The milligrams of Zombine in our system, well, that equals what we started with. Remember, the suggested dose is 65 milligrams. Multiplied by 0.57, because each day we keep 57% of the Zombine in our system, raised to the power of x, where x is the number of days, because that's how many times we multiply by 0.57. Let's use this equation to figure out how much Zombine will still be in our body after 32 days. We'll definitely be needing a calculator for this calculation. Right, 32 days, that's the x. So we want to figure out 65 times 0.57 to the 32nd power. Now on calculators, the exponent button, it looks different depending on the calculator you're using. In this calculator, it's the x to the y button. Let's see here. 1.0, a big long decimal, and then notice there's an e to the negative 6 power. Well, that means times 10 to the negative 6 power. So let me write that out and we'll talk about what it means. This number is in scientific notation. The 10 to the negative 6 power means we really need to move the decimal point to the left 6 places. So that would mean we'd end up putting 5 zeros in front of that 1. I'll go ahead and leave off the 002 because those are very small decimal places. We just figured out that we have 1/1,000,000th of a milligram of Zombine left in our system after 32 days. It's always important to answer word problems in the context of the situation. Other exponential decay situations behave the same way. Here's an equation we can use for any decay situation. A is what we start with. Well, r, that's the rate of decay, so 1 minus r, that's the multiplier. And x, well, that will be the time. And when you work that out, it tells you y. That's what you end up with. Let's give this equation a try with a different example. Here's a problem that's hard to solve with a table of values or a graph. It'll be easiest to use an equation here. A population of 218 rabbits decreases by 2% each month. How many rabbits will be left after 84 months? The equation tells us that after 84 months, there are about 35.9 rabbits left. Let's round that off to the nearest rabbit. In this lesson, we explored how to write exponential decay equations.